Thank you. First of all, I want to thank Dr. Abbas and all the organizers for this fantastic online workshop. And today, my topic is the multi-physics modeling of the human heart with SPHinXsys, an open source SPH library. And this library is teamwork, and I want to contribute all the members from our team. Okay, this is the outline. First of all, I want to introduce the validation of the SPHinXsys library. Then I want to talk about our recent work for the simulation of the hard modeling with our SPHinXsys library. Then I will give the mainly future work concerning develop open hard simulate based on the open source library. First of all, what is SPHinXsys? Actually, SPHinXsys is open source, meshless, multi-physics, and multi-resolution library. And the meshless meaning that we are using a unified SPH approach for the simulation of a multi-physics system, which consists of the fluid mechanics, elastic dynamics, and the fluid structure, and they are coupling with the multi-body solid dynamics. Concerning the multi-body dynamics, we are coupling same body with our open source library. And for the multi-resolution, we are using the different resolution for different subsystems. Also, we introduce a multi-time stepping method for the time integration. And you can find that through the GitHub and the YouTube channel. The first validation is the free surface flow, which is a benchmark of the Denberg flow. This is the video and the comparison with the experimental. You can see here in the present library, all the main features, for example, a long run up and a very large second jet, and all the other variant free surface is well captured and have a good agreement with the experimental. We also compare the surface evaluation and the pressure problem with the experimental data. As you can see that as the increase of the resolution, our data have a good agreement with the experimental data. I also want to note that in this animation, a very small number of particles is used. As you can see here, even a very small number of particles used, the simulation have a good fidelity. The second test is concerning the elastic dynamics. This is a benchmark widely used for the SPH method for the modeling of the elastic oscillating beam. We have to do the convergence study, also can compare our results with the analytical one. As you can see here, the results have a good agreement with the analytical one. We also used the SPH method for the simulation of the high velocity impact, which aluminum project impact on a plate. The velocity is about 4,000 meters per second. As you can see here, the main phenomena is captured by the present method. This is the simulation of the larger deformation for twisting cantilever with the initialization of the angular velocity. As you can see here, the particle method can well capture the larger deformation of the twisting cantilever. The third topic is concerning the simulation validation of the fluid structure interaction. This is a widely used benchmark for simulation of the FSI, where analytical solution is available. This benchmark test is studied by Abbas and other researchers in the literature. This is the two results. First one is with consistent structure resolution. Because in this simulation we use multi-resolution. The first test we set the structure resolution consistent with varying fluid resolution. This one is consistent fluid resolution by increasing the structure resolution. As you can see here, a high order convergence is observed for both tests. And also note that we run this simulation for a long time, for example, 5 seconds. The second is a widely used benchmark in the immersive boundary method, the fluid-induced vibration. This is the vorticity field with the deformation of the structure. This is the oscillation of the end of the beam, and we have done a convergent study. Also, we can compare our results with the data in the literature, as you can see here. For the frequency, while agreement is noted, and also note that the amplitude may vary in different methods. And then we want to show the coupling with the multi-body system. In this method, we coupling our library with same body for the simulation of the fluid interacting with the solid body dynamics. This is a very famous experimental, the oscillating wave energy converge, and this is set up. And we use the same body for the model of the solid dynamics. Here, the flap is pinned to a hanger, and with the interaction with the singular wave, the flap will oscillating in the simulation. As you can see here, even the simulation is 2D and the resolution is not so high. A small, obvious slamming phenomena is captured, but it's not so big compared with the experimental because we may have a higher resolution and a 3D simulation for the wave capture of the slamming phenomena. And a more complex is the coupling with the multi-body system. Here, the structure is elastic, and we study the passive flapping of the fish connecting to a fixed point through a steering cable. This is experimental. As you can see here, the dead fish can extract the energy by the deformation of the fish body. Then it will swimming forward. This is our simulation results. As you can see here, in the present method, the forward swimming is well captured. And this is the result of our GPU acceleration, and this is the animation of the slow phenomena. And this is the GPU and the CPU we are using, and we want to test the two cases with different particle number. And as you can see here, as the increase of the particle number, a very large speed up is noted. Also, with the help of the GPU, the simulation can be very fast. This is the start for the validation of our library, and then I want to talk about the multi-fix hard modeling. As we know that heart is the main function of heart is pumping the blood flow into the circular system. Actually, the underlying physics is very complex. It generally consists in the macroscopic scope force system. For example, the conducting system is governed by the mono or bidomain equation, which governs the propagation of the transmembrane potential. And then the transmembrane potential will induce the contraction of the myocardium. And the contraction of the myocardium will coupling with the opening and closing of the valve system for the injecting and filling of the blood flow. Meanwhile, the blood flow is governed by the hemodynamics model. Actually, it's a typical multi-physics problem, and it's related to our daily life. And concerning the electrophysiology, we consider the monodomain equation. This is the equation, as you can see here. It consists is a PDE consists of the diffusion and one ODE. This is the general form of the propagation of the transmembrane potential. After the steady state, a very steep increase is followed by a slow depolarization, and this is the basic structure of the conducting system in the heart. The stimulus will start as the SA model, and then it will go to the AV model, and through the percussion network, the stimulus will ejected to the myocardium muscle. And to close the monodomain equation, we have to apply several models for the ironic. And here, this two models we are using here. And we want to note that due to this very steep increase, this problem is very challenging to capture the fast dynamics characterizing the propagation. So this is our solution. We introduce operator splitting to split the ODE into one diffusion operator and 2 ODEs of reaction. And for the diffusion operator, we're using the anisotropic SPH discretization. And for the 2 ODEs, we introduce the reaction by reaction splitting combined with quasi-steady state solver. And as the QSS solver is based, actually is unconditionally stable. So therefore, we can use a very large time step for solving the model domain equation. This is the benchmark validation of the diffusion operator. We consider the isentropic and anisotropic diffusion. And you can see here, the method have a good agreement with the analytical one. And this is the free path. We initialize the transmembrane potential using this equation. And after that, you can see the proper equation of the transmembrane potential will in this profile. And here, a very steep increase, and then followed by a depolarization. This is the model we are using here, and we compare our results with the data in the literature. As you can see, the SPH method actually can do a very good job for the simulation of the reaction diffusion equation. And then we want to try to reproduce the spiral wave by using different geometry. For example, the square myocardium or the circular myocardium. This is the initial condition, and this is the spiral wave pattern after the simulation of different time steps. As you can see here, for different geometries, the prismats can reproduce a stable spiral waves. And we also compare our results at a time equal to 1000, these two figures, with the data in the literature. As you can see here, a very good agreement is noted. And then we will go to the electromechanics. This is a basic structure of the myocardium in the left ventricle. Here, as you can see here, from endocardium to the epicardium, several layers of sheet exist, and in different sheet, the direction of the fibers may vary accordingly. So this means that we have a very nonlinear and anisotropic myocardium dynamics to be modeled. Here we follow the total Lagrange formulation, and this is a particle kinetic model. And for the active stress, we follow the active stress model, which means that we separate the pure stress into two parts. First is the passive one, and the second one is the active one. This is the Gamma equation for the passive stress, and this is the Gamma equation for the active stress. Again, we have an active stress factor, which is governed by another ODE equation. And for the discretitation, we are using the total Lagrange formulation. Then we can using SPH unified SPH framework for the modeling of the cardiac electrophysiology, myocardium mechanics, and the electrofeedback. This is the test of the passive deformation by introducing the initial velocity in this direction with a cantilever. Here we're using two different models, the Neo-Hocken and the HO model. And this is the simulation compared with the data in the literature. You can see here the present method have a good agreement with the data in the literature. Here is the active of the, here is the simulation of the active stress. We consider a cubic myocardium, which have a consistent and a linear potential. And we introduce ad hoc activation law, which means that the active stress, which is linearly related to the transmembrane potential, and this is the deformation. This is undeformed geometry, and this is the isentropic case, and this is anisotropic case. We compare the displacement of the top panel to the data, which is obtained by FEM. Again, the method have a good agreement with the FEM. This case, we want to introduce two things. The first is the free path induced extraction of a biventricular heart. And the second one, we want to show that the present method can reproduce the scroll wave in a complex 3D geometry. here this is the geometry representation of the biventricular heart, and then we introduce a CAD compatible body conforming particle generator to generate a very how to say that fancy particle distribution. And this is the feedback direction at the epicardium, at the endocardium, follow the propagation of the myocardium. This is the two video show the contraction induced by the free path and the square wave. As you can see here, in two tests, the heart contract have a good, how to say, is contract according to the transmembrane potential. Okay, basically this is the main material we have here. As a concluding remarks, we have introduced the validation of the SPHinXsys library, and we also have proposed a unified SPH framework for the modeling of the cardiac electrophysiology, the cardiac electromechanics, and several experimentals have been studied for validating our library. The future work is concerning the open heart simulator based on the SPHinXsys. This is the work we want to do. First of all, is introduce the packaging network coupling the realistic propagation of the transmembrane potential, and this is the high resolution anatomic model we want to use for the simulation of a realistic geometry heart. Okay, this is the link to our SPHinXsys, and you can find all the tests in the